All right, there we go. Let's try this one more time. Good morning. This is the end of the course today, basically. This is today we're going to discuss sections 1611, 1612, and then I think for the last 2 days, I'm going to try to indulge myself. I think I usually would, or maybe I'll just ask. Maybe we'll take questions and then I'll indulge myself. That's good. Yeah, on Wednesday, on Wednesday, and maybe at the end of the day, I'll just sort of take questions on homework and whatever, and then after that, I will indulge myself and talk a little bit about sort of things related to my own research, which are actually tangentially related to Galois theory. Anyway, so today we're hopefully going to get to show that the quintic is insolvable. The take-home exam 3 is due on Wednesday. Oh, and I would like you to submit that on Gradescope. So there we go. Please submit the exam on Gradescope. Oh no. Scope. There we go. I saw a number of you tried that out, and actually, you want to say in the chat, does it work okay from the viewpoint of a student? When you submitted homework, that was like not too terrible. It was okay. So 1 yes. I'll take that as. So Mon, can we resubmit on Gradescope? Could you ask that out loud?
Oh yes, actually I just uploaded my homework 10, and I found there's one problem I want to rewrite, but I didn't see the resubmit button.
Oh, I think there's a way to do it. Just go and try to submit it again. Or actually, Mon, can you do that as an experiment for me? Just try to resubmit it, and if it works, great. And if not, let me know, and then I know that I can just delete your file, and then you can go resubmit it.
Oh, okay. Now or
after class.
Oh, okay, sure.
Or if you're really bored, that's fine.
It's fine.
To some extent, today is more conversational anyway.
Okay.
And thank you for DJing. That's the next choice of song.
Oh, you're welcome.
Okay, so any quick questions before we get started? Good morning, Robbie. I think that you're, yes. Well, good morning, everybody. Okay, so let's get started. Yeah, and Mungru, let me know how that turns out. I'm really curious to see how resubmission goes on Gradescope. That would be great. Okay, so right, Galois theory. That's right. So one last time, I think. Or maybe we'll summarize next time, even if we're just taking questions. So what is Galois theory? Well, let K be the splitting field of some irreducible little f and big F. The point is that Galois theory relates the field theoretic properties of. Oh my God, I'm never going to fix this little typo. Field theoretic property as K is an extension of F. For example, the degree, and the group theoretic properties of the Galois group of K over F, that is the group of F automorphisms of K. So in particular, G, we know that G permutes the roots alpha 1 through alpha n of your irreducible polynomial F, and is therefore isomorphic to a transitive subgroup of Sn. Therefore, it's not obvious, but it is true. The main theorem of Galois theory says that there's a bijective inclusion reversing correspondence between subgroups of G and intermediate fields between F and K, sending H to its fixed field and L to the Galois group. Again, as always, I'm going to make my little hand gesture. You send L, the intermediate field, to the Galois group of the big field over L, and not L over the base field, like you might think at first. In particular, if you want to understand and this will actually come up today, if you want to understand the Galois group of L over the base field, well, that's a Galois extension. Sort of the lower part is a Galois extension exactly when the corresponding subgroup the thing up here, the stabilizer of L is normal in G, in which case the Galois group of L over F is G mod H. All right, so and then sort of our immediate problem, of which we were dealing with, actually that's no longer our immediate problem. So but one sort of computational problem. I guess let me cross that out. So it's not really our immediate problem. It's really more what's really happening is that this is our computational problem. Oops. So our the computational problem that we consider is, which you've been doing all over the homework and also on the also on the take-home exam. This is sort of like if you get a PhD, this is exactly the sort of thing they ask you on a qualifying exam. Find the Galois group of x to the fourth of a splitting field of x to the fourth minus 2 and over the rationals, and draw out all the intermediate fields. This is like good stuff here. This is how it works. Anyway, so the computational problem that we sort of tackle first is that given splitting field, compute the Galois group and sort of draw out the intermediate fields and draw the correspondence. But the big finale for today, which I hope we'll get to today, I think we'll get to today, is the question of when is it that alpha 1 through alpha n can be written as a function of the coefficients of our original irreducible f in an expression that uses only sort of roots, kth roots. That's sort of a generalization of the quadratic formula. So if that's the case, then we say that f of x equals 0 is that equation is solvable by radicals. Otherwise, it's sort of not solvable. So the big result that people always discuss in relation to this, I think it was actually proven before Galois, but it was proven much cooler by Galois. And we should actually see a short proof. Well, relatively short proof of it today. It's only short because we've built the entire course, essentially the entirety of abstract algebra is built around proving this theorem. So it sort of makes it look shorter, even though the point is that you've really actually just put in a year's work to get to this. So the classic name for this is that I guess I'll make this purple just to kind of match what we're doing here. Here's a purple quote: insolvability of the quintic. Yeah. So the classic way to refer to this this result is the insolvability of the quintic. And so, yes, that's right. You've been lying to your college algebra and pre-calculus students. You can't actually solve. You can sort of factor stuff up to degree 3, maybe up to degree 4. There's some possibility. It's pretty gnarly. Go look it up on Wikipedia. I have only the faintest idea what that formula looks like. But yeah, when you get to the quintic, it's literally the only way. Actually, let me sort of put this in, because I think it's a useful way to think about this actually, which is that so the insolvability of the quintic means the only way to describe the factorization of f of x is the product of the x minus the alphas. Where the only way to describe actually yeah. Let me put this. Sorry, put this slightly. The only way to describe the alpha sub I, the roots of f, is the roots of f. So it's actually, and this is really startling. Actually, I think that I sort of first understood this when trying this out on a computational algebra machine. So I type in this insolvable, and I was like, oh, you can factor this. Like, what is it? What happens when you type in factors? And it just says it's the product of x minus the roots of roots of f, and there's no better way. And what the theorem actually says is there's no better way to describe it. So it's sort of like you have to, basically you have to invent a new kind of root for every equation. So yeah, so really factoring polynomials is actually pretty pointless. Uh, uh, sorry, college algebra and pre-calculus students. It's easier. On the other hand, it is easier than the thing that has some point, which is figuring out what you do with a factored version of it. But okay, that rant is for another day. All right. So any questions about what we're about to do in the big finale? One nice thing about lecturing from home is that you get to hydrate. Okay. All right. Let's move on then. Okay. Where were we? Yes. So I want to talk about Kummer extensions. So this is actually I think today this is actually going to look a little bit invisible. But this is actually a necessary step in the big finale. I'll sort of indicate, even though I won't go into details, I'll indicate where this theory is used, Kummer theory. So it's basically a theory of adjoining roots. So Kummer extensions. So to say that K is a Kummer extension of F means that we have a prime P, and F is a subfield of the complex numbers, and zeta is the P sort of standard Pth root of unity, either 2 pi I over P, and that's an F, and then K over F is a Galois extension of degree P. So to say that K over F is to say that K is a Kummer extension means that you have a Galois extension of a sort of prime degree over a field that includes the Pth root of unity. And so the theorem, the Kummer's theorem, says that if K is a Kummer extension of F, then K is F adjoin a root. So that in other words, the elements of K are exactly the F linear combinations of Pth roots of elements of F. Yeah, so there we go. Right. Actually, oops, that's not quite right. It's an F polynomial. My bad. Sorry, linear combination is just sort of a subroutine by now. Anyway, so as I was saying before, so rudely interrupted myself. Yeah, elements of K. The elements of K are exactly polynomial combinations of Pth roots of elements of F, which means that they. So the point is, yeah. Why did I put in that explanation? So the point is, so elements of K are exactly expressible in terms of radicals in elements of F. They are solvable, quote, solvable by radicals. Okay, yeah. So the point is that that elements of K that whenever you have a Kummer extension, if you assume that F has a certain number of these Pth roots of unity, which are sort of annoying, but okay, it's sort of annoying to have to throw them in, but you have to throw them in. Once you throw in those Pth roots of unity, then any Galois extension degree P actually has to be obtained by taking Pth roots. Okay, so how are we doing so far? Is zeta in the base field? Yes. Part of the assumption. So part of the assumption of the definition of what it means to be a Kummer extension is that zeta is in the base field F. So that's part of the definition of what it means to be a Kummer extension. So, Robert, that answer your question? So, Robert, did that answer your question, or is there? Yeah, okay, good. Any other questions about that statement? Very thirsty today. Okay. Okay, so let's go ahead and prove this because I think mostly because, as Artin puts it, the proof is pretty cool. Well, that wasn't exactly how he put it, but more or less that's what he said. Okay, so let's go ahead and prove this. So there's the theorem. If K over F is a Kummer extension, then K is F joined beta, where the pth power of beta is an F. So let G be the Galois group of K over F, which is cyclic because it's a group of order P. You remember how that goes. So the first claim is that if you think about K as a vector space over F, then sigma is an F linear operator on K. And why is that? Right, so what would F, so the point is for, oh gosh, what do base, for, I guess, right, so A and B in, actually, let me, so I guess for alpha and beta, oh, no, I don't have alpha, for gamma and delta in K and A, that's called C and F. So what we want to do is we want to show that sigma is linear. Right. So we got yeah. So this is this. So this what you know, if this all works out the way that we usually want, that we hope it will. This is part of the definition of F linearity, that sigma of gamma plus delta would be equal to sigma of gamma plus sigma of delta, and sigma of C, I guess, let me be optimistic. We want this to be equal to sigma of gamma plus, oh, actually, sigma of delta. So that's actually, this one isn't that hard. But the sort of amusing one is that this turns out to be eventually C times sigma of gamma. This one's a little more amusing. So, does that make sense? That if, so are there any questions as to why, if we can prove these two identities, that will give us, that's the definition, that will give us that sigma is an F linear operator, a linear transformation from K to itself over F? And actually, let me type out that conclusion. So sigma is a linear transformation from K to itself as an F vector space. Okay, so does that make sense, everybody? That those two identities are going to show that we can think of sigma as a linear transformation. Okay. All right. Well, the first one. Oops. Oh no. There's stuff in the chat. Oh, there's more yeses. Okay. So so the first one is actually basically that's the part of the definition of automorphism. Why is that true? It's because a sigma is a ring automorphism. The ring homomorphism. Right, but I mean it's a field automorphism of K, but in particular it's a ring automorphism, so that works. And now the second one is, well, it's not any more difficult, but it's more amusing by the definition of ring homomorphism. This is sigma of C times sigma of gamma. So that first one. So that first one is because. So this is here is because sigma is a homomorphism, is a ring homomorphism. Oops. There we go. All right, and then but then the cute part, I guess well, maybe I'm exaggerating the interest of how interesting this is, but I thought the cute part is that sigma of C is equal to C. Oops, let me do that. Because sigma fixes F. So the way we get from here to here is that because sigma fixes F, because it's an element of the Galois group, and the Galois group fixes elements of F. Sigma fixes F. Cute, huh? Anyway, so this indeed shows that sigma is a linear transformation, is an F linear transformation from K to itself. So is that good? I thought that was cute. So good. I thought that was kind of cute. Okay, so now we know that sigma is a linear transformation from the F vector space K to itself, and so we can use the power of linear algebra on it. All right, because right in particular, we're assuming that we are assuming that F, right. This is how this is where we have to use the subfield of the complex numbers. Now you can replace that with something else, but just I think it's reasonable. It's a reasonable shortcut to use. Say we're using complex numbers, so that means we can use. That means we can do linear algebra over C. We can use linear algebra over the complex numbers. And so that's the whole point of that part of that definition, assuming that that F is a subfield of C. So because, in any case, because sigma has finite order, sigma can be diagonalized over the complex numbers. So this is a fact. So I guess maybe I should talk about where that fact comes from. Comes from. I don't want to backtrack and prove it. So how many of you have heard this fact that if you have a linear transformation of finite order over the complex numbers, you can diagonalize it. So just show of hands or show of yeses and nos in the chat box. How many of you have heard this fact? And if you've heard about it, where did you hear about it? So just no. So yeah, if you could either respond, yes, I've heard about it, and blah, or no, I've never heard this. Okay, so that's, yeah. All right, so I'm just going to use this fact because it's a bit far afield for it. It's actually one of the interesting things about how Artin's book is organized is that it begins with linear algebra, and so a lot of the examples, actually sort of all the examples, involve this crash course in linear algebra, and which is pretty handy actually. As you might have noticed, I'm pretty fond of this book, I think, and not just because that's sort of where I took this. Anyway, here's a sketch of why this is true. Yeah, so why is it that finite order elements? So finite order elements elements whose power, who have some finite power equal to the identity, elements preserve an inner product. I bet that wasn't where you thought this was going, but yeah, that's what it is. Product. So so they're essentially so they're conjugate to Hermitian matrices and Hermitian matrices. So there, if you want to look up, so why is it that any linear transformation of finite order over the complex numbers can be diagonalized? It's that's the sketch of it. So because elements of finite order preserve some inner product, not the one you start out with necessarily, but you can sort of rig up a different one. And so up to conjugacy, up to a change of basis, they're Hermitian matrices, and Hermitian matrices are all diagonalizable. So that's the name of that tune. So that's where that comes from. Anyway, so the point is, because sigma has finite order, we can diagonalize it over the complex numbers, and where the diagonal entries are going to be the eigenvalues, the diagonal entries like that, are going to be the eigenvalues of sigma. And so, which means the eigenvalues lambda, must satisfy lambda to the p equals 1, right? Because remember, sigma has order p. They can't all be 1, which means that sigma has some eigenvalue lambda not equal to 1, such as that lambda to the p is equal to 1, i.e., the point is that lambda equals zeta to the something. Oh, those p-th roots of unity are so useful. Right. So the point is that lambda is going to be one of those p-th roots of unity. I guess I should say k not equal to 0 mod p. Let beta be an eigen. So if there is an eigenvalue, there must be a corresponding eigenvector, and so let beta be an eigenvector. Right? How does this go? So sigma is a linear transformation on K, and we think of K as a vector space over F, and so vectors are going to be elements of K, right? And so if we have an eigenvector, it has to be an element of K, and it has that eigenvalue lambda not equal to 1, and let B be the p-th root. B be the p-th power of beta. Well, on the one hand, sigma of beta equals lambda beta, which is not equal to beta. So beta is not in, oops, I'm getting ahead of myself. Did that in the wrong place, my bad. Maybe, no, that's fine. So sigma of B equals sigma of beta to the P, which is equal to sigma of beta to the p-th power, because sigma is a ring homomorphism, which is equal to what was sigma of beta? Sigma of beta is an eigenvector of sigma. So beta is an eigenvector of sigma with eigenvalue lambda. So this is going to be lambda beta raised to the p-th power, which is equal to lambda to the p times beta to the p. And lambda to the p, we just said, fortunately I fixed that typo, lambda to the p is equal to 1, and so this is equal to beta to the p, which is equal to b. And so remember, one of the great properties of Galois extensions is that elements of the fixed, well, is that the fixed field is equal to the base field, and so beta is in the fixed field of G, and so beta must B is in the fixed field of G. Ugh, my bad. So let me try. Let me rewind that 30 seconds. So yeah, so B is in the fixed field of G, which means that B is yeah. So let me type that out. I.e., B is in the fixed field of the Galois group of G. And therefore, which means that B is in the base field by the fixed field theorem. Furthermore, if we look at sigma of, if we look at sigma of beta is equal to lambda beta, which is not equal to beta, because lambda is not equal to 1. So beta is not in the fixed field of G. So beta is not in the fixed field of G. And so beta is not. This is like actually one of the great. This is lovely proof, isn't it? So this is one of the great sort of techniques of Galois theory, especially as practiced by people who who have to do this, like solve problem sets and exams and stuff. Is that if you want to figure out if something is in the base field or not, spin it around by some. I mean, it's not just the thing for solving problem sets. It's actually the thing for solving problems. So if you want to figure out if an element is in the base field, you spin it around by the Galois group. If it is completely unaffected by the Galois group, then it has to be in the base field. If it's moved at all, if any element of the Galois group moves that element, then it can't be in the base field. Anyway, so beta is not an element of F, and which means that when you look at F adjoin beta, that has to be something bigger than F, but there's no way to fit, since the degree of the extension is prime, there's no way to fit something strictly in the middle, and K is equal to F of beta. Hooray. Yeah, so yay. Any questions? I mean, the result isn't maybe so well. It is. We'll sort of see what this has to do with solving things by radicals in a minute. But as you may have seen in the reading, but I especially think this proof is pretty cool. So, we good? Any questions, or you ready to move on, or do you have questions? Okay, so let's talk about. So yeah, I have to say I don't know this very well, so I apologize for any mistakes here. But I'm just basically copying this from Artin. As an application, we have Cardano's formula for the roots of a cubic. So just some notation here first. So let omega be the standard cube root of unity. The degree of q adjoint omega over q is 2, because 1 plus omega squared is 0. This is an identity very close to my heart. Well, for general general values of 2 and 3 here. All right. So suppose we have oh yeah, let me remind you that you can put everything, that if you have an arbitrary cubic, you can put it in this form, and thus somewhat simplify a lot of the formulas, as you may vaguely remember. So remember that this is what all cubics look like by a change of variables. So you can do a change of variables and make the squared term go away. Anyway, so suppose f of x is in that form is irreducible over, in that form is irreducible over big F with roots u1, u2, u3, and discriminant d. So let K be the splitting field of little f over big F. Right, and I guess one reason for having 3p here instead of p and 2q here instead of q, which remember that was the way it usually goes, is that you can sort of factor out the junk and discriminant, you get like q squared plus p cubed. And as you'll see, it sort of it'll fix some problems later on. Clean up the formulas later on. Oh, right. It cleans up some formulas later on if we went on with the details, which we're not going to, because it's in Artin and they're not super duper interesting. All right. Anyway, well, but the point is that for us is that there is a formula. Okay, so by the Galois theory of cubics, we know that the splitting field of K over the rationals has degree either 3 or 6. And remember, there's sort of two cases here. This is the A3 case, and this is the S3 case. Which means that if you look at the degree of K over F, which is going to equal the degree of K over Q times, which is, and remember this is, well, I should write this out. This is the degree of K over Q. Oops. Yeah, that's what I want to do, sorry. K over Q divided by the degree of F over Q. There. And this thing, this degree over here, this latter degree is 2. And so the only way, the only thing that's got to be left here is so this is going to be degree 2. And so what's left over here for the degree of K over F has to be 3. And so now we have, K is an extension of F that is a right. Yeah. So it's a Galois extension because K. Yes, I'm getting confused here. So and I know I'm getting confused. I'm getting confused because I've forgotten to draw the tower of fields. There we go. And so right. And so the point is that if we think of the degree of K over F, then that has to be 3, and has to be a Galois. It's a splitting field, and so it's a Galois extension, and so we finally have, and so yes, we have the Kummer thing. All right, so and we know the permutation sigma, which sends the roots U1, that sort of cyclically permutes the roots of F. Roots U1, U2, U3. That must be in the generates, actually generates the Galois group, because the Galois group has order 3. And furthermore, if we just happen to write down these two elements, Z and Z bar, so those two are those two elements, Z and Z bar, are eigenvectors with eigenvalues omega and omega squared, respectively. So by the proof of Kummer, it must if you go back, not just to look at the statement of Kummer, but actually the proof therein, it must be that Z cubed and Z prime cubed are in F. Whew. All right, so we have these. Now we have these two random elements that are in F. So is everybody good with that so far? Maybe I just did that a little quickly, maybe a little confused. But so any questions about the part up to the point where Z cubed and Z prime cubed are in F? Yeah, let me go back to, let me just go back and indicate one more time. Right, so if you have so what the proof of Kummer says, which we did over here, is if you happen to have an eigenvector of that sigma with with the eigenvalue not equal to 1, then its cube, then it is not in the fixed field, but its cube is. Okay, so in other words, these are cube roots of elements of F. But now, if you look at Z plus Z prime, oh, I really like this part. So this is going to equal to U1 plus omega U2 plus omega squared U3 plus U1 plus omega squared U2 plus omega U3. And let me remind you, as we saw up here, that omega plus omega squared is equal to -1. Oh, I'm very fond of the cube roots of unity. Yeah, so omega plus omega squared is equal to -1. And so this is equal to 2u1 minus u2 minus u3, because omega plus omega squared is equal to -1. And then what's the last thing we want? Oh yeah, and then one last note here. Oops, I want this to be, so under this assumption, now we did need this to simplify what we're about to do. Under this assumption, our first symmetric polynomial in the roots is going to be equal to 0. Or in other words, if we start with the form x cubed plus something x plus constant, then we have that u1 plus u2 plus u3 equals 0. Right, the sum of the roots is 0. So the fact that there's no square term over here means that the sum of the roots is 0. And so what that means is that u1 is equal to u2 minus u3. This is actually equal to u1. And so we see that this is equal to 3u1. So yeah, so again, the sum of z and z prime is 3u1, and so 3u1 is the sum of two cube roots of elements of F. And so that sort of tells us, yeah, there we go, that the root that root of that equation, u1, is equal to 1/3 times the sum of two cube roots of elements. And then if you sort of carry out the details, and which you can see in Artin, at least to some extent. So details omitted. But if you carry out the details of that, then eventually you get an actual honest-to-God formula for the cubic, for the roots of the cubic. But details omitted. So yeah, so here is in this sort of nice way we recover a very old formula. I guess a formula for the roots of a cubic, which sort of way predates. I don't know how Cardano did. He was probably like beat it to death by sheer cleverness. But yeah. Anyway, so the point is this gives, and if you carry it out, this gives this tells you that there is some formula for the roots of the cubic in terms of cube roots and square roots. And if you're very careful, you can actually sort of carry out the details and figure out what that formula actually is. I can see I should have left more space on this slide. Oh well. Anyway, but there is, at least there is. So are there any questions about the fact that there is such a formula? Okay. So 30 minutes. Can we prove the insolvability of Quintic? I think we might actually. We'll get close anyway. Let's do it. Solvability. We'll get close because we're going to leave out some of the details. All right, and so this is, right. As you know, I rarely depart from Artin, but this is actually going to be a slightly different approach from Artin. And actually, if you compare what Artin does, you'll see that because I think at heart am a non-commutative person, a non-abelian person, and so I'm going to do things more on the group side of things and less on the field side of things. The proof in Artin has a lot more on the field sides of things, and also more details. Okay, but here's the idea. On the plus side, I'm going to introduce you to. Oh, right, and maybe you actually did this. Did you guys do solvable groups in 221A? So can everybody say in the chat whether you remember discussing solvable groups in 221A? Yes, no? Oh, you did. Okay, so the term came. Okay, I will remind you of it momentarily. So I'll remind you of the definition of a solvable group, and then you'll see why it is. I think I would guess, think that whoever gave you the definition said, oh, maybe you'll find out later why they're called solvable groups, and that time is now. So here we go. They're solvable groups because they correspond. What we'll see, the thing we're going to show here is that they correspond exactly to the equations that are solvable by radicals. So that's where the term solvable comes from. Okay, or if you're British, soluble. That happens. Yeah, I always got to do everything different. Okay, so again, in order to, so yeah, we're going to assume that our base field is a subfield of complex numbers, and the reason that we can use Kummer. That wasn't so readable. Yeah, so we will somewhat harmlessly assume that F is a subfield of C, and that alpha is an element of F. So so the theorem says the following three conditions are equivalent, and I think so. Artin sort of generally, and so just to tell you what's different what we're going to do today from what's in Artin. So Artin mostly uses the equivalence of 1 and 2, and I'm going to talk about condition 3 here. So the first condition says that there's a chain of subfields. There we are. So the first condition says that there's a chain of subfields from the base field to this full extension K, such that alpha is in K somewhere, is at least at the very least in the big field, and each successive field extension is obtained from the previous one by joining a pth root. Oh yeah, for p prime. I should say for some prime p. So alpha is then solvable by radicals expressed in terms of radicals. Yeah. So right. So this is sort of the condition that we, I guess, want. If you want something like the Quintic formula, which the non-existent Quintic formula, then that's what you'd want is situation number 1, where you can sort of make a chain of subfields and and get that each of which is obtained by taking pth roots of the one before, and so and if you that's exactly when you can find some expression for alpha in terms of radicals. All right, so I hope that makes sense. So that's condition number 1. That's the one we want if we want to find some generalization of the quadratic formula. So here, this one, this here's another condition, again expressed for some prime p, for some prime p. So another one is there's just a chain of subfields starting from the base field and adding another one and adding another one. So that's another chain of subfields, such that alpha is is at least in the top one and sort of in the end results. And at each stage, each extension is a Galois extension of the previous one with of degree p for some prime p. And all right, and yeah, so I think the part we're going to gloss over, because it actually is kind of glossed over in Artin, is that the equivalence of this thing here, that's where we use Kummer theory. Oops. Let me type that out so you can actually read it. So there is where Kummer appears. And yeah, so I think I'll just leave it at that. So the equivalence of 1 and 2 is that's the reason we want I wanted to mention Kummer theory, right? Because I think it's maybe yeah. So Kummer theory gives 1 implies 2. So so what I actually want to talk about is how 2 implies 3. And actually, what we really want, because we're talking about the insolvability of the quintic. So let me talk about why we're really more interested in 1 implies 3 and not the other way around. So because given 1 implies 3, if f of x equals 0 solvable by radicals, then the Galois group of k over f satisfies condition in number 3. And what is that condition number 3? Let me see, did I plan this out? Oh yeah. Oh right. I should actually now draw a picture that describes condition number 3. Okay, so go. All right, so let me go back and actually just read it. Let's read what it says. So there exists a chain of subfields starting from the base field and then first extension, second extension, all the way to extension number t, which is the full field k, such that alpha is in k again. And for every step in the middle, let's see, let me draw this. So right, oh gosh, how's this? So the big group, right. So so let me draw this here. Right, so it's always the big group, the small field F0 corresponds to the big group. And so this is going to be your G of K over F0. That's going to be our sort of full group G, is what we're thinking. And then what we need, the condition number 3 says that each of the right, because as the fields get bigger, the groups get smaller. Fields get bigger, groups get smaller. And so this is going to be, so what happens is that each succeeding Galois group K over F1 is a normal subgroup of the previous Galois group. G of K over F2, and that goes all the way down to, so there's a slight subtlety here. And let's call this like H1, H2, all the way up to what's the last one? Well, I guess the last one is the identity. Well, I guess that's traditional. G of K over Ft, which is, I guess I'll call that HT, but HT is, Ft equals K. So this is just the identity subgroup, the trivial subgroup, because Ft equals K. All right, so good. So does this look vaguely familiar? So remember this stuff from 221A. Yeah. So and this is called like, oh my gosh, a subnormal something or other. I never think about this stuff. It's a subnormal chain or series or something like that. My aphasia is kicking in here. This is a subnormal. I think it's a subnormal series. Oh yeah, and the point is, not only is this is a subnormal series, and each quotient. So it's a subnormal series where each quotient is a finite cyclic group of prime order. We call a group that has such a subnormal series a solvable group. A finite solvable group. There are also infinite solvable groups where you don't require the quotients to be finite. That you just need them to be abelian. For infinite solvable groups, we only require quotients to be abelian. And actually, if the reason that we can assume that the quotients, I guess I should type this out. So we can take, in the finite case, in case of finite G, we can assume we can take all the quotients, the prime order, because if we have an abelian group of non-prime order, we can sort of dissect it. We can sort of cut it into prime order pieces. And I guess, yes, I've written one paper about where I actually had to use a subnormal series and in group theory, and I never did that. I've never done that again. I'm not particularly good at it, but okay. And this, I guess I know how to do this. But yeah, so I'm gonna guess that either you talked about the sort of cutting into smaller pieces. That's just an aside, but in any case, we can just take the definition of solvability to be that you can sort of find a subnormal series for each of the sort of quotients. So this is so this is sort of, yeah, this is, so I guess we should also call this H0. And the point is that Hj mod Hj minus 1 is cyclic of prime order. Not all the same prime, but for some, I guess really I should say the C sub Pj or something like that. Whatever. Okay. So does that sound thankfully this is vaguely familiar, I hope, but does it sort of make sense, that description of condition number 3? So is that okay? Okay, so yeah, so right, it's this sort of slightly specialized finite version of the definition of solvability. Okay, so let's prove 2 implies 3. That's the main point. We have this chain. We have F0 is a subfield of F1, is a subfield of yada yada, up through Fs, which is at the top. And the point is that we're assuming that Fj over its previous thing is a Galois extension. So now remember the normal subgroups portion, part of the main theorem, or at least that chapter on the main theorem, but it's really sort of part of the main theorem of Galois theory that says, I mean, that was a sort of a nice completion of the theory, but it's also very useful in this particular circumstance, because the normal subgroups part of the main theorem of Galois theory says that, so remember, these are the poorly behaved ones. So remember, the things that sort of go down, sort of, anything involving an intermediate field in the top of the chain works okay. So as long as you preserve the top, you're looking at the Galois group at the top of the chain, that's okay. But it's the things that are sort of in the middle, that, or from the middle to the bottom, that might behave poorly. So, but if this is actually Galois extension, that says that, so Fj mod Fj minus 1 is a Galois extension if and only if the corresponding let's see. So the bigger, right. So what do we want? So the smaller subfield has the bigger Galois group. So so this has to go like G of K over F sub J minus 1. And so, so the theorem says that that Fj is a now we're thinking about, so for the when we apply this, so when we apply this, we're now thinking of Fj minus 1 as our base for this little chain of reasoning. So if you think of F sub J minus 1 as the base field of the splitting field K, then applying the normality part of the main theorem of Galois theory says that F, the sort of intermediate field, I should draw this again. So K, here we're thinking K is an extension of Fj, an extension of Fj minus 1. So remember that this stage of things down here is a Galois extension exactly when the corresponding subgroup, the Galois group of K of F over J, G of K over Fj is a normal subgroup of G of K over Fj minus 1. And that is, yep, there we go. That's condition number 3. And furthermore, oops, what a weird color. Why did I decide to make that olive? Furthermore, in that case, G of also from the normal part of the main theorem. We have that that G of Fj mod Fj minus 1 is isomorphic to the corresponding quotient, G of K over Fj minus 1 mod G of K over Fj. Oops. There we go. Here's a better looking G. And this group over here, we is sort of assuming too. Oops. The extension that we have over there has degree p, so this group has order p, and therefore is cyclic of order p. There we go. We're done. That's it. Easy peasy. That wasn't so bad. So there we go. So yeah, so solvability, I mean, assuming this is sort of part that I left out, which is sort of the less fun part, I admit. It's in Artin, but yeah, it's sort of less fun. So, but essentially the equivalence between, the equivalence of 1 and 2 is essentially Kummer theory. Now we've proven the more fun part, which is that or at least I find it to be more fun. I'll be honest. That if you have this chain of subfields where each of which is a Galois extension of the previous with prime degree, then that must correspond to exactly your Galois group, your overall Galois group being your overall Galois group being solvable. So we say like here, the overall Galois group is solvable. G is solvable. Okay, so so are we good with the idea that if our equation solvable is, if our equation is solvable by radicals, then the corresponding Galois group must be solvable? So is that idea okay? So we're good? All right, so now the big finish. Drum roll, please. Here we go. So that was less spectacular. Okay. So here are some facts, which are not well. There are nice proofs of this, but let me talk about how to prove this by brute force. So fact, A5 is simple. Oh, you guys did. Wait. A5 is simple, and S5 is almost simple. So did you guys discuss this in 221A? Or should I briefly indicate how to prove that? An ugly proof of this. So did you guys talk about in 228? Yes, yes, no? Okay. All right, so here's the reason why. Here's one reason why. So if k is if you have a polynomial little f over big F, and the Galois group of k over f is either a5 or s5, and the roots of f are not solvable of little f are not solvable over big F, and the proof is just that that a5 is not solvable, for example, because the only possible subnormal series for A5 is this. Right? A5 has no non-trivial normal subgroups, and so the only way to set up a subnormal series for A5 is that, and S5 is not solvable because all you can do is this. I mean, I guess like the last quotient is abelian, it's because it has order 2, but yeah. So somehow that non-abelian simple group A5 just sort of creates a blockage that prevents anything that involves A5 from being solvable. Okay, yeah. So yeah, as soon as you have that sort of non-abelian simple piece in there somewhere, you can't get rid of it. So that's it. That's the proof. I mean, it's only short because you spent your entire year setting it up. Okay. Oh yeah. And so one other fact. So if G is a subgroup of S5 and G, so now we're gonna actually. Oh yeah, the grand finale because I've run out of slides. There we go. So here's one more fact. If it's transposition, let me remind you this what transposition looks like. So the fact is that G contains a 5 cycle in transposition, then G must contain all of S5. That's actually one reason why S5, the only normal subgroup of S5 is the only interesting normal subgroup of S5 is A5. So as a corollary, if you have an irreducible f of degree 5 over q, and k is a splitting field of f over q. And if f has exactly 3 roots, then the Galois group of k over q is S5. And so proof of that, so one point is that complex conjugation. That we know that's a field automorphism. So we asked many times, like, well, how do you know that something's a field automorphism? Well, one way to know that something's a permutation is a field automorphism is if it's induced by something by a sort of something that we already know is a field automorphism. So complex conjugation induces transposition. So if there are only 3 real roots, there are 2 conjugate complex roots. So complex conjugation will induce the transposition on the complex roots, on the non-real roots. I guess they're all complex roots. And G must include a 5 cycle because those are the only, because 5 is the order of G, and 5 cycles are the only elements order 5 in S5. So G is not, there we go. And so that proves that G is S5, and so this particular polynomial x to the 5th minus 16x plus 2, which you can find has 3 real roots by graphing. 3 real roots by graphing. Oh my, more or less. I mean, you could be fancier about it by using the intermediate value theorem, but 3 root roots because you get by using your graphing calculator. and is irreducible by the Eisenstein criterion. Oh yeah, remember I promised that we would use that at some point? No, well, here's the one point where we use it, but it's very useful. I guess you sort of use it a couple other times to prove that things are irreducible. There we go. You cannot solve the equation x to the fifth minus 16x plus 2 equals 0 using radicals. Okay, thank you for your patience. Sorry I went over time by 3 minutes. I think we ran out of time for questions, but I will just sort of start here again next time and take questions about this and anything else about Galois theory. And thank you for your patience. We did it, Brooklyn. We did it. Okay, we survived. Anyway, and then I will kind of indulge myself for the rest of the semester. Okay, so thanks everybody. Bye.